Power is a measure of how fast work can be done. So in an equation form, power equals the amount of work that's done divided by the amount of time that it took to do that work. Power equals work divided by time. When a system has more power, it's able to accomplish more work at the same amount of time, or it can accomplish the same amount of work in a faster amount of time. For example, a worker who runs up a flight of stairs uses more power than the same worker who climbs the same set of stairs slowly. The amount of work, which is the effort to lift the worker's weight to a certain height, is the same in both of those examples, but the amount of time is different. The standard unit of power is the watt, and a watt is 1 joule per second. Remember, joule is the unit of work, second is the unit of time. So work per time, joule per second. Another common unit for power is the kilowatt. And then, since power is work divided by time, and we know that work is a method of transferring energy, so you could think of power as the amount of energy transferred divided by time. Therefore, if you want to know the amount of energy that something uses, and you know the power of the system that's transferring that energy, then energy equals power divided by time. Oh, I'm sorry, I said that wrong. Energy equals power times time. So common units of energy are, of course, joules, which is what we've been using most commonly. But you could also talk about energy in terms of kilowatt hours. That's kilowatt times hours, because that's a unit of power, the kilowatt, times a unit of time, hours. Okay, there are several examples for us to go through in the student packet in section F, which starts on page 25. And so let's work through some of these examples together. In number 1, it's talking about a tugboat that's moving a cargo ship. It applies a huge force, 3.5 times 10 to the 8th newtons, to move a cargo ship 500 meters, and it takes 20 minutes to do it. So if we wanted to calculate the power of this tugboat, we have to calculate how much work it's doing and then divide by the amount of time that it takes to do that work. In this case, because they give us a force and an amount of displacement, we're going to calculate the work as F delta X. And so let's see. Let's check our units as we plug in. So I have 3.5 times 10 to the 8th newtons and a displacement of 500 meters. Here's where our units are not in standard. Units. They're giving me 20 minutes, and I really need seconds. So 1 minute is 60 seconds, and so that would be 1,200 seconds. 20 minutes is 1,200 seconds. So if I do this math, I get a very huge power rating, but this is a big tugboat applying a lot of force. I get 1.458 times 10 to the 8th watts. Okay? In number 2, we have Jill pulling on a rope to lift this bucket out of a well, and she's applying a constant force as she pulls up at a constant speed. And we want to know how much power is required for her to lift that bucket 3 meters in 5 seconds. So the system is the pail and the earth. And we'll assume that at the beginning, where it is, we'll call that a height of 0, but it's 10 meters higher at the end after Jill has pulled on it. So the work that Jill is doing is changing the gravitational potential energy of this bucket. So the power is going to be the amount of work that she's doing divided by time. Now, they didn't give me a force and a displacement, but I can tell the power because the work that she's doing is changing the gravitational potential energy, so I can calculate that power as the mgh of that bucket. And it's a 12 kilogram bucket that's being lifted 10 meters, and it's being done in 5 seconds. So that's 235.2 watts is the power that Jill is demonstrating there. I'm going to skip 3 for the sake of time, but let's look at number 4. An elevator is pulled up at a constant velocity, and it takes 3 seconds to travel a distance of 4.5 meters. So there is a little bit, I mean, it's not on the ground at the beginning, it is higher at the end, and the difference in that gravitational energy is due to the work that the motor is doing on this elevator. It's applying a force to pull it up. So the initial gravitational energy equals the final gravitational energy plus the amount of work that was done. Or the work equals, in this case, the initial minus the final gravitational energies. They gave me the mass as 515 kilograms. And the delta H in this case is is 4.5 meters. So just taking it as a snapshot view, it's being moved up 4.5 meters, and so the total work that is being done on this elevator is 22,711 joules. So the power is calculated by doing that much work in the 3 seconds. Which is 7,570.5 watts. Let's skip number 5. Let's look at 6. So here we've got another elevator. It starts at rest on the ground. So at position A, there's really no mechanical energy. But at position B, which happens 30 seconds later, it says that it has a velocity of 1.8 meters per second, and it's reached a height. So it has both gravitational potential energy and kinetic energy. And the energy that we see at position B came through the process of working. It was transferred into the elevator system from the motor. So the work that the motor did equals the change in the kinetic energy plus the change in the gravitational energy. And so we want to figure out the power of that motor. Well, first we calculate the work. It's the kinetic energy plus the gravitational energy. And they gave me the mass in kilograms and the velocity in meters per second. And they gave me the height in meters. Everything is standard units. So if I calculate the work that was done, I get 36,738 joules. The power of the motor is that amount of work divided by the time that it took to do it. And it took 30 seconds. And so we get 1,224.6 watts as the power of that motor. Let's skip down to number 9, please. I think that 7 and 8, although interesting, are not very typical of the kind of problems that will be on our test. And so for the sake of time, let's go on to number 9. Here we have a power plant that's supplying 1,100 megawatts of power to the electric grid. And we'd like to understand that in terms of the joules of energy that it's supplying every second. Well, I know that 1,100 megawatts, maybe it'd be good to just go ahead and convert that to watts. And there are, mega means multiply by 10 to the 6th. So 1 megawatt is 10 to the 6th watts. So this power plant is supplying let's see, that'd be 1.1 times 10 to the, I think that's 9. Yes, 10 to the 9th watts. And so we'd like to know how many joules of energy it's giving us every second. Well, we know that 1 watt is 1 joule per second, and so that must be 1.1 times 10 to the 9th joules every second that are being provided by this power plant.